And we're live.
Very basic, simple, kind of like just putting a steak on the barbecue with no seasoning. The steak is still good. Selling the sizzle, not the steak. Hey, our next unit, forces. And those who take Physics 12, you're going to find, if Curtis had still been here, he just left, he would tell you that's one that we really flogged to death because almost everything for the rest of physics comes out of our understanding of this. So I called this one, Lesson 1, Introduction to Forces. We're going to start off with some terminology. What's a force? There's a fancy schmancy physics definition, but I'm going to say to you, you know what? A force is a push or a pull. If you're pushing on something, if you're pulling something, you're applying a force. Okay, there are exceptions. It can get more complicated, and we're gonna start there. Force a vector or a scalar. Well, if you push on something, does it make a difference what direction you push on it from? I think it does. So if I can have Rob, who is shaking his head. Rob, come stand here, please. Quick, quick, quick. Alex, stand up. Dane, stand up, please. Here's how I can convince you that force is a vector. Stand like this. Put your hands against both hands against him. You're going to face him.
Is he going to hurt me?
You're going to face him. Both of you push. Right now, Rob's not accelerating. He's not moving anywhere. Stop. Alex, get behind Dane so you're in the same line, same direction. Now both of you push. Okay? If you notice, the direction made a difference. Completely different outcome. Force, vector, or scalar? We've reasoned our way. What is it? Vector. Let's circle vector. You guys can sit down. Vector. Symbol for force, capital F. Oh, it's a vector, so often almost always you'll see me put a little vector sign above it to remind myself of that. And again, I hope you've picked up, I'm not taking marks off for sloppy vector notation. What I want to use vector notation for is to remind myself to make sure I do the physics correctly, especially those of you that take Physics 12. You're going to find it becomes a very, very handy memory trick. Hey, remember direction, remember. It's going to be a difference here. What do we measure force in? Well, in the old imperial system, force is measured in pounds. That might lead you to think that force is measured in kilograms in the metric system. It's not actually. Kilograms is not a measure of force. It's actually incorrect physics, but society is doing it wrong, and we have to live with that. Force is measured in newtons. Named after a scientist whose last name was? Newton, Sir Isaac Newton. Symbol, capital N. You learning? Here is my way of convincing you that force is a vector. I'm asking you to find the net force in the following diagrams. The net force, that's a fancy way of saying if you added up all of the forces on an object and represented them with just one force, we call that the net force. So if you're pushing 5 newtons and 2 newtons to the right, what do you think the net force is? Direction. 7 newtons right. B. What do you think the net force is here? Think about it. 3 newtons to the right. Is that okay, Jeff? This is what I was trying to illustrate when we were pushing on Dane. Force is a vector. Makes a big difference which way you push or pull something. C. What do you think the net force is here?
0.
That's going to become a hugely important situation. If I know my net force is 0, that lets me make a lot of assumptions, and there's an easy way to tell if something's net force is 0. We'll talk about that. What about D? In Physics 12, we'll say, okay, what if everything isn't in a nice straight line? What if some stuff is horizontal and some stuff is vertical? What now? We'll introduce an entire branch of mathematics called vector mathematics. We'll actually look at it a little later on this year. We'll touch on it this year as well. And we'll learn how do you add 6 newtons right plus 3 newtons up. And there is a way. It's a whole new mathematical rules, but it can be done. That's Physics 12. Newton's laws of motion. I got to go on my Sir Isaac Newton rant. I got to pause the video. Put your pencils down. So let's talk about Newton's laws of motions. Newton's first law, often called the law of inertia. And it says this. I'm going to give you the formal language, and then I'm going to give you a better, easier way to remember it. In the absence of an unbalanced net force, in other words, if your net force is 0, no problem, an object will either remain at rest or move in a straight line at a constant speed. Or I can reverse that. If an object is accelerating, and now you guys know what acceleration means, it means it's changing its speed or it's changing its direction, because acceleration is a vector. There must be an unbalanced force. I got to fix that. Force, change that word to force. Whoops, acting on the object. Say what? Let me clear that up. So write that down and then look up for a bit. Basically, it says this. Are you accelerating? If you are accelerating, then situation C is impossible. You must have an unbalanced force. If you're accelerating, it has to be situation A or B. When you add up the forces, it can't be 0. Oh, if you're not accelerating, then it must be situation C. But remember, not accelerating can mean two things: standing completely still or moving in a straight line at a constant speed. Both of those are not accelerating. V can be constant or 0. And that then explains this rolling the ball. When you roll the ball, is it slowing down? There must be a force acting on it in the opposite direction. There has to be, otherwise it wouldn't come to a stop. Which force, Sally? Friction. She's doing physics 12 at the same time, so she's seen some of this already. Friction, we're going to talk about that force. This explains an awful lot about car accidents, and other stuff. So, you've been in a car before. Your body it possesses inertia. Another word for inertia is mass. Objects with bigger mass have bigger inertia. We'll write that down later. So your body has a lot of inertia. It wants to keep going in a straight line at a steady speed. That's why when you go around the corner, your body feels like it's moving sideways. It's not. The car is actually moving sideways, and your body wants to keep going in a straight line at a steady speed. In the pre-seatbelt days, back in the 60s, when cars had front row bench seats, guys, I kid you not, if you were going out on a date with the girl, you would buy some surfer's wax, and you would wax down the passenger seat. And then what you would do is you would hold your hand like this, and you would make a hard right turn, and because you'd waxed the seat, she would come sliding across into you, and you would say, "Oh, hi, honey, that's great." And you put your arm around her. It was a night. Ask your grandparents. I bet your grandfather might even admit to that. Talk to your grandparents. That was what was done. That was not what was happening. The girl was continuing in a straight line. The car was actually rotating underneath her, because Newton's first law, inertia, says she wants to keep going in a straight line. And because she was sitting on a really, really slick seat, there was no way to apply force on her. So imagine you're a passenger in a car, and the driver makes a sudden left turn. What sensation do you feel during the left turn? You feel like you're getting pushed to the right. I did do my rant the other day about your bodies being opposite accelerometers. So you feel like you're being pushed to the right. You're actually being accelerated to the left by the car. Contrary to what your common sense might tell you, you're not being pushed to the right at all. The driver steers the car to the left. Your body wants to keep going in a straight line. You feel like you're being pushed against the door. Actually, the door is pushing against you to keep you going around the corner. Otherwise, you'd keep going in a straight line. How many of you have ever run when you're sharing rides? You run and you want to get the front passenger seat. What do you shout out? Why? Because that's a terribly morbid joke from the 1950s and 60s. Before seatbelts were mandatory, the front passenger seat was called the shotgun seat because if you were in a car accident, you were the first one out to inspect the damage, was the joke, because you were going through the windshield. So you'd be the first one out, and as you were passing over the hood, you'd inspect the damage. You'd be dead, of course. It's called the shotgun seat because it was the launching seat. Why? Car comes to a stop, but what does your body want to do? Keep going in a straight line? a steady speed. As a general rule, turn the page. As a general rule, any object tends to continue moving with whatever speed and direction it presently has. In fact, if it's not moving in the same speed and direction, I guarantee there's an unbalanced outside force acting on it. That's Newton's first law. Are you changing speed or direction? The fancy word for that is, are you accelerating? Then you have an unbalanced outside force. If you're not, you don't. This can include zero speed, of course. When your driver accelerates the car, your body tends to stay where it is. That's inertia. It wants to stay at a speed of 0. The seat has to apply a force on you to push you forwards. That's why you think like you're accelerating. You feel like you're accelerating backwards. You're not. What you're really feeling is the car pushing you forwards, the same as when somebody pushes you in the back really quickly with 2 hands. This tendency that all massive bodies have to resist change in their motion state or in their state of motion is given a special name. This is what we call inertia. Every object in the universe that has mass has this property of inertia. In fact, for the purposes of physics 11 and 12, Trish, we're going to treat mass and inertia interchangeably. The more mass you have, the more inertia you have. The less mass you have, less inertia you have. And that's true almost always. In fact, one way you can think about this, inertia can be thought of as the measure of the laziness of an object. The more massive an object is, the more lazy it is, the less it wants to change. Its resistance to change. Hey, which object has more inertia, a bicycle or a logging truck? Logging truck. A logging truck. And because it has so much more inertia, the logging truck is A, more difficult to get moving because it wants to resist change more than a bicycle. So if you want to get it to accelerate, you need to pour in on a lot more energy. More difficult to stop because once you get it moving, it wants to keep going in a straight line at a steady speed. And more difficult to turn at a corner. How do we measure inertia? Mass in kilograms. How does Newton's first law help explain how seatbelts save lives? Well, we just talked about that, the shotgun seat. So all a seatbelt does is because your body wants to keep going in a straight line at a steady speed, the seatbelt says, I'm going to apply a force in the opposite direction to bring you to a stop. Why don't we put seatbelts on motorcycles? Why don't we put seatbelts on motorcycles? Or have I just come up with a brilliant Nobel Prize winning invention? I haven't. Why wouldn't you want a seatbelt on a motorcycle? Yeah.
Because the motorcycle could go on top of you.
Okay, the motorcycle wreckage is so small, it doesn't have much inertia on its own. In fact, it has approximately the same amount of inertia as you. It's going to slide, it's going to come to a stop at about the same acceleration as you, and there's the risk that it tumbles and lands on top of you. Absolutely. Okay. So how does Newton's first law help explain how seatbelts save lives? Seatbelts apply a force to bring you to a stop. Otherwise, you can put in quotes, shotgun. That's why that joke is still with you from the pre-seatbelt days. All of you yell it out. Maybe you've never realized it was a gallows humor, morbid joke back in the 50s and 60s. You're in the shotgun. Simple invention, the seatbelt. So I've been in 3 car accidents in my life. I'm going to tell you about the second one. The second one was during my student teaching. I got rear-ended by a semi-truck on the freeway. It was pretty serious. My mom, as a matter of fact, when she came to pick me up, started having a bit of a panic attack because she looked at the car and she was wondering how the heck I survived. I survived just fine. I think I banged my knee. I was driving an old little Honda sedan. I got rear-ended by a semi-truck. So the semi-truck applied a force to my vehicle, and my vehicle then, because it didn't have much inertia compared to a semi-truck, went flying into the vehicle in front of me. It was stop-and-go traffic. It was right just before the Burnett exit, and I guess the semi-truck driver had just looked down to pick up his cup of coffee, and he was very apologetic, and he came and helped me right away and didn't deny anything. Everyone was fine, which is always the important thing in a car accident. But here's the physics. I had an ashtray, and at that time, I kept all of my change in the ashtray. There was probably a handful of quarters and dimes and nickels. And when I got hit by the semi-truck, that ashtray change went shooting over my right shoulder and hit the back seat. No, it didn't. That's what it appeared relative to me, relative to my velocity. What had really happened was that ashtray had enough inertia, similar to what we just did with the water container. My car got pushed forward, and it wanted to stay where it was. My car got pushed forward, the ashtray stayed there, and then dropped to the ground behind me. Newton's first law. Inertia. There was some friction because the ashtray, but it was a nice loose ashtray. It came out really easy. That's my car accident story. I have some video examples as well. So video example of Newton's first. Good demo. Hail and stay dry because of physics. Woohoo! Car accident story. Next page. Manuel weighs 1,000 newtons, because that's how we measure force, in newtons, not in kilograms, and stands in the middle of a board that weighs 200 newtons. The ends of the board rest on bathroom scales, and let's assume that the weight of the board acts at its center. Let's see if we can use what we've learned about physics to fill in the correct weight reading on each scale. First of all, look at Manuel and the board. Are they accelerating? Are they sinking into the ground like quicksand? Everybody say no. Are they lifting into the air like Superman? Everybody say no. That means the net force on them has to be 0. What's the total downwards force? Add it up looking at the picture. 1,200. What must the total upwards force be then? 1,200. Are they standing dead center? Take a guess, do the physics. How much do you think each of those upwards forces on either end must be to get 1,200? 600 apiece. So far, so good. How do I know that? Newton's first. It has to be. Otherwise, he would have to be sinking into the ground like quicksand or lifting into the air like Superman, because Newton's first says if you're accelerating, there's an unbalanced force, and if you're not accelerating, the net force is 0. It's a very powerful way to describe motion. And again, way ahead of its time, because what he was really doing was visualizing outer space back in 1580. Hey, example 2. When Manuel moves to the left as shown, now the scale closest to him reads 850 newtons. What must the weight on the far scale read? Got to be 350. Why? Because if it didn't, he's either sinking into the ground like quicksand or flying into the air like Superman. A 12-ton truck is 1/4 of the way across a bridge that weighs 20 tons. A 13-ton force supports the right side of the bridge as shown. How much must the support force be on? So here we're doing some bridge engineering now. First of all, is the truck and the bridge sinking into the ground like quicksand? Is it lifting into the air like Superman? Then what must the net force be? 0. This is also, by the way, why force is clearly a vector. So what's the total force down? 32 tons. What must the total force up be? 32 tons. So what must the support on the left be pushing up at? Must be. Oh, and if it can't handle that, you better not design this bridge. It's part of the bridge engineering. Some of the stuff you start to look at. That's Newton's first. Newton's second law is the equation. It tells us how to calculate force. It's going to be your main equation this unit. It's on your formula sheet, but I guarantee all of you will memorize it. In fact, if you don't memorize it, Curtis, is he making it okay? I think he needs a little help, Curtis. Give him a little elbow. Okay. If you don't memorize this is my way of knowing you haven't done any of the homework. It says this: F equals ma. Although Sir Isaac Newton was much more interested in acceleration, so he actually, when he gave us this equation, got the A by itself. Look at that equation. How would you get the A by itself? A equals what? F over, okay, that's what he said, but whatever. We all say F equals ma. F equals ma. Force equals mass times acceleration. Where mass is in kilograms and acceleration. Oh, did we just finish a whole unit on acceleration? Now you know why. Okay. This also means that 1 Newton equals, well, F equals ma. What are the units for mass? Kilograms. What are the units for acceleration? Meters per second squared. And so 1 Newton is actually 1 kilogram meter per second squared. And in fact, that's what it was called for a few hundred years. But a few hundred years ago, we decided to name this unit after Sir Isaac Newton. Hey, he wrote the book on it. Let's name it after him. Instead of saying kilogram meters per second squared, which is what it is, let's just call that a Newton. Less writing. Malcolm has a mass of 65 kilograms. What's the magnitude of the gravitational force acting on him? What does it want me to find in this question? A word that begins with F. Well, F equals ma. What's the mass? What's A due to gravity? We're going to ignore the negative and just put a 9.8 in because I said magnitude. I didn't care about direction. Is that all right? In fact, often you'll see this. The force of gravity, will often write it as mg, where g is 9.8. You'll start to see me, you'll notice me doing that over the next few lessons. Anyways, what's the gravitational force? If you weigh 65 kilograms and you're standing on your legs are experiencing a force of 637 newtons. That's the force of gravity. And the force of gravity has a special name. We call the force of gravity your weight. And this is a problem. To the non-physics person, if I say, what do you weigh? You're going to tell me an answer in pounds or kilograms. That's wrong. What do you weigh should be in newtons, and it's mg. So it's your mass in kilograms times 9.8 if you're here on the Earth, times something else if you're on a different planet. Your mass never changes. Your weight changes depending on where you are in the universe. So I am on your test for this unit, not your test for Thursday, but on your test for this unit, going to ask you questions about weight. Newton's